All right, in this lesson, this is 10.1, Operations with Matrices. We are really going to be focusing on addition, subtraction, and scalar multiplication. All right, so in this example, we're going to talk about scalar multiplication. So notice they've given us a thread that is talking about prices at a clothing store. And for the sake of your notes, please label this as prices for women's clothing before you write the matrix. It tells us that columns represent vintage, casual, and distressed, and that the rows represent jeans and jackets. So jeans would be your first row, and jackets would be your second row. So we need to have those labels. It says if the sales tax rate is 5%, how can we use matrix operations to find the amount of sales tax on each item? So what we can do is we can represent this as 5%, which is 0.05, times our matrix C, or 0.05, and then we can write the matrix itself. And this operation is performed honestly kind of like how you would expect. It's almost like distribution. This scalar value is going to multiply by every single entry of the matrix itself. So I'm going to pause the video and show what that result would give. And so what this represents then in context of this problem is that these output values are the amount of sales tax that would be applied to the original values. So you can see this would be really helpful if we were talking about a large amount of data from a company and you were wanting to apply something to like an entire spreadsheet, for instance. That's where this kind of concept would come in. So 2 notes that I want you to add to your notes about scalar multiplication. And that is that in scalar multiplication, the size of the matrix does not change in the end. Notice that I had a 2 by 3 in the beginning, and I have a 2 by 3 in this output. And also, each value in the matrix is multiplied by the scalar variable, just like distribution. Okay, so now let's talk about addition and subtraction of matrices. I would like for you to copy down these 2 matrices and label them as A and B. So let me zoom in so you can do that. Here's A, and here's B. And so now we're going to use those to answer a few questions. So the first thing says, what is the total sales for the 2 months? All right, so to find the total, we can add these 2 things together, and that can simply be written as A plus B. Now remember that these numbers actually represent something. They're not just numbers sitting there. So in this example, I think it's jeans and jackets, and then there's different styles, vintage, casual, and distressed. So it's important that we keep the values in the same places so that we're adding corresponding things. So when I'm finding the sum here, my resulting matrix is going to be the same size. And so for our first spot, I will add 14 and 18 together, and that's going to give me 32. Then I will add the 11 and the 17 together and get 28. And next I will add 28 and 25, and that will give me 53. Pause the video, see if you can get the last row. All right, and so for this, you should have gotten 26, 24, and 80. And so what this does is gives you the sum that you're looking for the 2 months, but it gives it to you in an organized way so that you still know which values correspond to which things. So for instance, you could still tell me what's the total sum of distressed jackets, and that would be 80 down here in the bottom. B is asking for the difference. So for difference, that means we're going to be subtracting. And again, this would kind of go as expected. Make sure that you subtract in the order that you've been given them. So for instance, the first one will be 14 minus 18. So that's going to give me -4. Then we'll do 11 minus 17, so -6. And if I continue this pattern, these are the results that I'm going to get. Make sure that you understand where these numbers are coming from as you're writing this example down in your notes. Okay, so we're going to talk a little bit more specifics about addition and subtraction. So notice this first set, A, B, C, and D, and think about which of these do you think could be combined using addition or subtraction. And you should notice that one of them is going to stand out here. B is a different size than A, C, and D. And so you wouldn't be able to match corresponding parts up, for instance, for A and B, because the 3 wouldn't have anything to align with. Similarly, you're going to end up having a row down here for B that doesn't exist on A. So what we need to note is that matrices must be the same dimensions to add or subtract them. And so as you're writing your notes, this is something you should just put a star next to. I don't even know that you need to give examples, but you can if you want to, and just show that you could not add A and B. All right, the next bullet point that we need to note looks at this example B, and it says, how can you interpret a matrix of zeros? So notice that it is possible to add two matrices together and get a completely zero matrix where all entries are zero. And that is referred to as a zero matrix. So far you've probably got 2 bullet points going on here. All right, now we're going to talk about something called the additive inverse. So they want to know in this case the additive inverse of matrix B. And so the additive inverse is going to be basically what you would think of, the opposite of when you add. So the additive inverse here would be -6, -5, 2, 0, -3, and +4. Because when you add these two things together, you will end up with a zero matrix. So these things are the inverse of each other. Basically, they will cancel each other out. All right, so there's our third bullet point. And then lastly, I don't even know how much of this you're going to copy down. You can probably copy some of it down, but it says, how does A plus C relate to C plus A? So if we add the two together, and I'm just going to show you this, notice this is A plus C, and here's C plus A. Because you're adding the corresponding parts, it doesn't matter what order you do them. So the whole purpose of this is just to show you that it does not matter the order you add matrices, but not all operations can be done in any order. So I would write that down. Addition is commutative, but not all matrix operations are. So what that means is A plus C does equal C plus A. Okay, so in this last example, it's going to be more important than you think, so please make sure you take good notes on this, because we're going to circle back to this a few times. So this is an example of using matrices to translate and dilate figures. So first you should write down these words. AB is translated to create PQ, so that means AB is translated to create PQ, and then XY is a dilation of 1/2 for AB. So this is 2 different sets of transformations, but they're both stemming from AB. You should also have this diagram drawn. I don't really care about like the XY axis labeling, but you need to have the different coordinates given because that will be relevant. So the first thing we need to do is we need to represent AB as a matrix. So I'm going to do that using in this instance, a square matrix. X will go on the top and Y will go on the bottom. Think of this almost like a horizontal table. So if X is 2, Y is 6. If X is 8, Y is 4. So this is going to be the matrix that I use for AB. And to represent the translation, I'm going to do AB plus. This says I'm moving 4 to the right and 2 up. So if I'm moving 4 to the right, that means my X needs to be adding 4 both times. And so I'm going to write 4 in 2 places because I'm adding it to all those values of X. And the Y moving up 2 will add a 2 to the Y values. So this is that translation. And that will create PQ. And notice when I add this, I'm going to get 6, 12, 8, and 6. And that corresponds with those ordered pairs I was given for PQ in the beginning. 6, 8, and 12, 6. All right, and then I added these notes if they're helpful for you about why we're picking those values. All right, and lastly, talking about dilation. So dilation by a scale factor of 1/2, that should make you think about scalar multiplication. So I'm going to do 1/2. Which is 2, I wrote that backwards, 2, 6, 8, 4. And if I apply scalar multiplication, that's going to give me 1, 3, 4, 2. And if I go and check my original graph, I should see the points 1, 3, and 4, 2, which we do see that is the points here of X and Y that we were given in the beginning. All right, so that's addition, subtraction, and scalar multiplication.